Attitude and orbital control is an important subsystem in spacecraft development, with many smaller subsystems within this field. In this presentation, we will focus on how the control moment gyroscope plays a critical role in maintaining spacecraft orientation. This is a presentation by
Garima, Tayo,
Mary, and Alexa. A control moment gyroscope, or CMG, is an attitude control device that is used in spacecraft attitude control systems. The first control moment gyroscope was launched in 1973 on the Skylab. 3 were included on board for system redundancy and the ability to apply correctional torque in any direction and along any axis. The largest competition for a CMG is a rotation wheel. A CMG consists of a spinning rotor and one or more motorized gimbals that tilt the rotor's angular momentum. For the purposes of this project, we are focusing on a single gimbal CMG. The 2 components consist of a rotor and gimbal. The gimbal rotates the rotor along an axis perpendicular to the rotor's spin axis. As the rotor tilts, the changing angular momentum causes a gyroscopic torque that rotates the spacecraft. The CMG's main purpose is to provide attitude control for a spacecraft. The CMG's ability to provide a high amplification in output to input torque makes it useful in larger spacecraft where larger internal torques are necessary to enable a change in attitude.
For the coordinate frames involved in the system, the gyroscope has a local coordinate frame that accounts for the torques due to the disturbances on the system, causing the coordinate system to undergo a rotation sequence based on the gyroscope's spin, precession, and nutation. Additionally, the spacecraft has a separate reference frame, which is related to an inertial reference frame, defined by the capitalized X, Y, and Z. This is established in order to relate the information of the spacecraft and the gyroscope reference frames. One of the governing equations is the Euler equation, which shows how omega is a function of the torque applied to the system. Here, omega is defined as the angular velocity of the gyroscope with respect to the inertial reference frame. Also, omega is defined by the rate of change of the Euler angles of the gyroscope, given by psi, phi, theta, or spin, precession, and nutation, respectively. The inputs of the system are the torque applied to the system and the rotation rates of the gyroscope. Since the angular momentum of a control moment gyroscope remains constant, disturbance torque applied to the system causes the gyroscope to precess. Also, as a result of the applied torque to the system, the reference frame of the gyroscope undergoes a rotation sequence caused by the Euler angles of the gyroscope. The resulting outputs of the systems are the changes in the angular velocity of the system over time due to the torque applied on the body, which ultimately determines the resulting attitude of the spacecraft over time. Additionally, by measuring the Euler angles due to the applied torque, the system establishes the new attitude based on the rotation of the spacecraft.
The measured quantities in the system are the rotation rates or the Euler angles changing over time. This is what the gyroscope will use to fix the spacecraft's orientation. The following block diagram shows a simplified description of the components in a CMG. When the spacecraft changes its orientation, sensors record the rotation rates and send those to the gyroscope's angular velocity sensor. From there, the gyroscope will apply an opposite torque to maintain the spacecraft's desired orientation. This is accomplished by sending signals to the rotor and gimbal motors. Overall, the goal of the gyroscope is to resist changes in the spacecraft's motion.
A feedback system takes desired outputs, compares them to actual outputs, and generates an error that is going to be corrected. This is a challenge for CMGs because they need to be stabilized for a wide range of operation in a spacecraft, which is essentially attitude control. One of the ways this challenge is solved is through the linear parameter varying gain scheduling technique. It is implemented on a closed-loop system, and it deals with parameterizing a nonlinear system in order to make it linear. Scheduling variables are involved in order to determine the current operating region of the system and to enable the appropriate linear controller.
A gyroscope has its own feedback control law, but overall it is part of the spacecraft's PID control law. PID stands for proportional, integral, and derivative. This is related to reducing the error between the spacecraft's current and desired orientation. The gyroscope calculates the derivative portion of the error. A separate feedback control loop is used to spin up the rotor to the required spin rate and maintain it. The control law brings a rigid body to rest at the zero altitude aligned with the reference frame.
The CMG system is discrete. This means that a certain amount of data points of angular velocity are recorded. For example, instead of having a continuous span of data, we get values like omega equals 0, omega equals 5, and omega equals -5. These signals are then used to calculate the input torque, which can be seen on the figure above. This figure shows data before the discrete signals are corrected or filtered. The discrete signals cause a lot of noise in the data for torque, but filtering occurs in order to make this data continuous. This goes hand in hand with the control laws and feedback system because data needs to be corrected in order for the gyroscope to do its job of stabilizing the spacecraft.
Bias stability is a measurement that describes how the bias of a gyroscope may change over a specific period of time under fixed conditions. Bias is the average output recorded when gyroscope is not in rotation. It is one of the smaller components of an error function, but system designers look for the bias stability specifications when deciding on a gyroscope to use. To be able to say that the gyroscope is performing correctly, we want that error value to be low. The performance metric of attitude and orientation asks the following questions. After the gyroscope rotates, is the spacecraft facing the way we want it to now? What is the error in relation to where the spacecraft is and where we want it to be pointed? Again, we want this error value to be low.
Sometimes errors with a spacecraft are caused by temperature. As a result, it is a common practice to vary the temperature to compensate for errors caused. Sometimes this works to mitigate errors, but other times temperature was not the error factor. Finally, vibration rejection is the most critical reason a gyroscope can suffer. Low-cost gyros are designed using simple mechanical systems and therefore suffer greatly due to vibration. Higher-cost gyros are less susceptible to damage relating to vibration, but it is still the largest error factor. A common strategy to remove this sensitivity is to add a mechanical anti-vibration mount to the gyroscope.
Thanks for tuning in!